In this video, I will walk you through my data visualization project on the topic of climate change. The story I am telling here is simple. It's a causal story or claim that human activity lead to CO2 emissions. Those emissions cause global temperature rising, and the rising temperature causes natural disaster to increasing both frequency and intensity uh, or severity. So to tell this story, I use three data sets from authoritative data sources. The first is the NASA's GISS, um, global temperature anomaly data. Um, it has the how global and regional temperature deviates from the baseline, which is the average temperature between 1951 and 1980. Um, it has a global northern, southern hemisphere and zonal breakdowns across 14 latitude bands. The second is the CO2 emissions data from our World in Data. It covers 215 countries from 1960 to 2024, with almost 13,400 country years records and 79 variables, including emissions by fuel type, per capita emissions, and GDP, and population, and other stuff. The third is the ENT DAT, um, natural disaster that's it. Um, it has all the 15,000 plus natural disaster events from 1980 to 2025. It records other stuff, for example, how many deaths, how many people affected, how many, what the total loss in economy in CPI adjusted. Uh, all of those tests are real, and let's jump into the how we did the data pre-processing. Um, for the NASA GISS temperature, the the thing is simple. Uh, we load uh, the three files, the which are the global, uh, uh, the northern and southern hemispheres. In the loading, the first thing we do is to skip the first row, which is the text header, and then we manually add the header. And for we have the three asterisks thing used as missing data. We convert them to not a number by trying to convert them into numerical using PD dot to numeric, and using the flag errors equals squares means any error is considered a not a number. So after loading all of the global northern and southern hemispheres, we add a hemisphere label table, label column. Then we load the zonal files, and which use like 14 zones, latitude band zones, for more granular analysis. Uh, and nothing. Yeah, this is the after processing data. For the CO2 emissions, um, we have 50,000 records. And the thing is, uh, the records has aggregates, for example, the world, high income countries, stuff like that. We want only the actual countries' data. So we filter by uh, records that has a true ISO symbol for the country, and for the year we chose from 1960 onward. And for the CO2 emission column, it should have some data. It shouldn't be empty. And yeah, this resulted in 13,400 plus usable records across 215 countries. Now let's go to the here also just like worth mentioning the top 10 countries in emissions, which is China, followed by US, India, and so on, with China having uh, 12,000 tons of emissions, which is almost three folds the second, and it has more than one third the emissions from among the top 10 countries. Now let's go for the disaster. Uh, for the disaster data, uh, it requires like minimal pre-processing. We just load the Excel file, and then one of the things we need to do is converting the economical damage, the CPI adjusted from thousands of dollars to billions of dollars by this simple equation across the whole column. Um, and Also we filter by the uh, climate related, um, let me say, natural disasters. We define those five types of disasters: the extreme temperatures, the wildfire, the droughts, the storms, the floods, as climate related or high temperature related. And yeah, the result is simple. We have now like 15,000 total events from 1980 to 2025, and with 47 columns. These are the whole disasters, and those are the regions, and so on. Now let's jump into the visualization, and let's go for the first visualization. Uh, let's go for the first visualization. Here, it's the global temperature anomaly bar chart. Yeah, this is a simple bar chart. It has the how much the temperature is deviated positively or negatively from the baseline, which, as I mentioned, is 1951 to 1980 average. And as you can see, as I hover here, till like 1940s, it's been like almost 1940s, and before it's been always negative. And after the 1977, 1980, it started to become only positive. One of the things I want to focus on, and this is an interactive chart, let's focus uh, on this specific time interval from 2000 till 2025. As you can see, it's all red, which means an elevated temperature from the baseline, and it's all increasing. This is a trend, like it's increasing, it's oscillating, but increasing generally. And with 2024 having the maximum deviation of plus 1.28 degrees Celsius as the maximum global average recorded. Yeah. Um, so, like, this is Blotley, and you can do the range slider as here, and this is handy interactive visualization. Let's jump into the second visualization. I want to focus here, which is the hemisphere temperature comparison. Like uh, this is a breakdown of this uh, of the global into of the global average into the north and south hemisphere averages. As you can see here, we have two kind of things. We have the solid lines and we have the dots. The dots are the raw data scattered here. For example, each dot is specific data reading for a specific year, either for global or for northern or for the southern hemisphere. And for the solid lines, they are the 5 year running average across the perspective region or global. And as you can see, consistently after 19, let me say 20s, something, the uh, the northern hemisphere has. Let me hide those. And let's focus on the northern hemisphere. Also here, it has this drop down. I can choose global only or north hemisphere only. But since I want to compare, let me put all of these. Let me hide those and focus on the running average. Generally, the northern hemisphere has, let me say, bigger temperature anomaly compared to the southern and has compared to the global, and in the same time, this is I can say this is due to the fact that the north part of the Earth is mostly land as compared to the southern part, which is mostly ocean. This help temperature to get elevated more in the northern hemisphere. Let's go for the. Uh, I think this is all about temperature. This graph is I don't see any. Yeah, let's go for this graph. Yeah, this graph is interesting. This is the uh, like latitude band zonal breakdown, and uh, it has this. As you can see, as you go north, the north bands are generally having higher average anomaly as compared to southern parts. But let me focus on two things. Let me focus on this Arctic band and the tropic band, which is the equatorial. As you can see, we have what we can say here, the Arctic amplification, which makes the North Arctic band to have three faults the anomaly in the tropics band, which is the equatorial band. This is interesting. Like the north uh, pole of the Earth is warming way faster than the rest of the Earth. This is what I wanted to say. Next, uh, let's go for the CO2 emissions, and uh, let's go for this interesting uh, uh, bar chart race animation. Let me run it. Okay, here, this is a simple bar chart, but it has animation that you can run, and you can clearly see uh, which bar is displaying in terms of info, like which country is this bar for, how much is the emission in this current country, in this current year, and what the population, what is the CO2 per capita emission, stuff like that, and the GDP for the country. And as you can see, let me run this. As you can see, United States was dominating from the 1960s. At the around the 1980s, China started to jump, and in the early 2000s, like eventually 2005, 2006, China overtook the United States, and the 2024 it's as the biggest, uh, almost one third the Earth emissions of CO2, and it has three folds, almost three folds of the United States emissions. And this is interesting. Let's go for the uh, let's go for the up next. The for this, I don't want to stop here. Let me go for the next one. Let's go for the okay. Okay, yeah. This is the total versus per capita CO2 emissions. This is one of the most interesting in this study. Yeah, it has it has a toggle that toggles between two views: the total emissions view and the per capita, which is the how many tons emitted per person in that year. Okay, this is interesting. Let's see here. In the total emissions, we have the China has the clear largest emissions, and but let me click on the per capita. The story completely changed. Look, here the United States has 14.2 uh, tons per capita, while China has almost half of that, which is 8.7 per capita emissions compared to the US. And India, which is in top 10, has almost one seventh of the United States emissions, which is like 2.2. And Saudi Arabia, which is ranked I think the eighth uh, among the top 10, has the biggest per capita emission of 20. And yeah, this is interesting. This reveals what I can, what we call equity emission dimension, like how much you emit per person in this country. uh, and this is reminds me of the Mantner's concept of manipulating the views by changing the encoding channel, and this is one of the interesting examples here. Let's go for the uh, two next visualizations. Let's go for the seventh one, which is the natural disaster sunburst, which is a hierarchical drill down that has the disaster type in the middle circle and or the inner circle, and the breakdown of that specific uh, type in the outer circle. And this is interesting. Let's for example, let's focus on this flood thing. When you click, you have, yeah, this Asia is dominating with over 190 total death and almost zero point 0.9 trillion in terms of total damage. If you go for another one, for example, uh, for the earthquake, or again, Asia is dominating with like almost half billion total death and um, uh, more than 1 trillion total damage. By the way, it's worth mentioning, this is tracking all the 15,400 plus events. Uh, if we go for the next visualization, the disaster frequency over time, let me rerun it. As you can see here, among the five disasters, we have the floods and storms as the biggest, and they always have been the biggest, but they have been increasing. But someone could say that, hey, the extreme temperature and the wildfire are more temperature anomaly related. Why they are still small? They are still small, but if we do a comparison, let me compare these. Uh, if you can see here in the beginning, the the extreme temperature has only three number of events compared to, for example, 39 flood events. In the 2024, we have 50 extreme temperature events compared to 144. So the extreme temperature events increased 17 times or more, while the the floods increased only less than 4 times from the beginning of data collection, which shows the the effect of extreme temperatures. The next, we have this interesting heat map. This is one of the most interesting things. This gives you the summary of the NASA GISS global temperature anomaly. It has the x-axis has the months and the y-axis has the year, and as you can see, we have uh, this color definitions, like which define the extreme red as positive, extreme blue as negative, and white as let me say near zero. As you can see, it's clearly that the the whole world is going from uh, yellow zone, from blue zone to extreme red zone, from 1880 to 2020 to 2024. And if I hover over any of the years, uh, any of the months, it gives the average monthly temperature and in that specific year. And this is interesting. Like imagine you read a whole data frame in front of you by using this simple heat map. The next is the how temperature, and this is the meat of this research or this project, is how temperature is related to natural disasters. And this is done by frequency or correlation plot. It has the year presented as color from purple, which is the 1880 thing, till the 2025, which is the yellow, white yellow, or the bright yellow. And in the x-axis we have the temperature, and in the y-axis we have the frequency of the natural disaster events. And as you can see, we have uh, uh, this OLS trend line, which present a clear positive, statistical positive correlation between the two. And the other thing is that as we go from uh, left to right, like as the temperature increases, we notice the circles are becoming bigger and bigger. And please note that the diameter of the circle is uh, the damage in billions of dollars. So as the temperature goes on, the frequency of events becomes bigger, and uh, the damage associated with those events is bigger, which is summarizes what we wanted to say. The last, but the most important, one of the most important, is the what I call um, the multi-panel dashboard, which has all the info about. Let me run it. Um, all the info about the global temperature anomaly, the CO2 emissions from the top three countries, the climate disaster frequency by type, and the economical damage from disasters per each year. And if you, as you can see, they respond simultaneously, where you can read data from multiple viewpoints for a specific year. And you can also, of course, do whatever range you want for uh, for the for those events. And this is um, what's called linked multiple views in the textbook. And as you can see, like as temperature rises, as emissions increases, temperature rises, frequency of events increases, economical damage becomes bigger and bigger. Um, and to summarize, this project used 11 interactive visualizations built with Plotly in Python, employing techniques including range sliders, drop-down menus, toggle buttons, animation, some burst drill down, heat maps, scatter plots, and thread lines, and linked multi-panel dashboards. All data is sourced from the sources I mentioned, NASA, our World in Data, and e, EM Data, EMDAT. The key takeaway here is that interactive visualizations transform abstract climate statistics into an explorable story. When where user can shift perspective, drill into details, and discover uh, patterns that static charts would miss. Thanks for watching, and that's all.